Thank you very much. And thank you all for joining. I know this is quite late for some of you and quite early for others. And I think it's really, really nice that Tavy is organizing that we can meet in the cyberspace to talk glaciology. So I really am grateful for the opportunity. And Tavy asked this in the summer, and I thought this was long ahead. And 1st of December is actually the Independence Day of Iceland. So we thought it was quite appropriate that we get a talk from Iceland on 1st of December. And in addition, we have quite exciting news. So I want to give away sort of like the exciting part of the talk, which I will try to keep to the very end. But I want to give you a little bit sneak peek already that we have observed, and I think Eyjólfur is online, and he's been observing the Grímsvötn Jökulhlaup starting. And it was quite funny that Eyjólfur was giving a talk, I think it was on Friday, 12th of November. And then he said that it was imminent that Jökulhlaup would be starting. And we see from the data that was probably around the time he was saying that the subglacial lake was starting to leak. And I'll show some of Eyjólfur and Krista's figure from both the ice shelf. They have a GPS instrument showing how the ice shelf is changing elevation when the water is going out of the subglacial lake. And then we also have now the water actually getting into the river. So there is a webcam showing that there is increased water levels. And in the news, actually, just about an hour ago, the news said that the water level had risen about 1 meter already. So we have ongoing Jökulhlaup in Iceland, as well Independence Day, and a talk from Iceland. So I think that's a quite good Icelandic advertisement for today. So just to bring you to the glaciers in Iceland, so hang on. I would just want to give you a very brief overview. So glaciers in Iceland are situated in a maritime climate. So we have high precipitation, all the low pressure system coming up towards the north along the Atlantic Ocean. They dump the precipitation mostly on the south coast. So that reflects the location of the glaciers in Iceland on the south coast and sort of towards the central highlands. But north of there, that's very dry, but we have quite a few mountainous glaciers in the northern part of Iceland. Do you see my pointer here, or is it here better? The laser pointer. Yeah, it's there. And so up here we have quite a few smaller glaciers, but 4 large ice caps that are larger than 500 square kilometers. Those are Vatnajökull, Hofsjökull, and Drangajökull, and Mýrdalsjökull. And the total area is more than 10,000 square kilometers, and that is about 10% of Iceland. And the volume is so much that if we distributed it over the whole of Iceland, it would be about 35-meter layer of ice covering the whole Iceland. And translated into sea level rise equivalent, it's about 1 centimeter. And to put that into context, about 40 centimeter is the sea level rise equivalent of all the glaciers outside Greenland and Antarctica. So 1 out of those 40 centimeters is Icelandic volume of glaciers. And the glaciers are going all the way from sea level to the highest peak in Iceland. So we have Breiðamerkurjökull here on the south coast, entering basically a lagoon that is at sea level. And the highest peak is at more than 2,000 meters elevation. So the elevation range here is 2,000 meters, and we have glacier covering the whole range. And the storage of the glaciers, or it stores about 20 years of precipitation. So there's actually quite a big reservoir, water reservoir, stored in Icelandic glaciers. And just to give you some sort of quick look at or aerial photograph, I show here one from Sólheimajökull on the southern coast of Iceland. And what I was trying to think earlier was that we want to show, and this is what all glaciologists in the world have been doing lately, is to emphasize that the glaciers are retreating, and actually quite fast. And all over the world, we see that they are reducing their volume and responding to the warming climate that we are experiencing all over the world. So this is an example. This is Hofsjökull, and this figure is taken by Oddur from an airplane in 1985. And you can see a few things here. The glacier is coming down from quite a big ice cap. So this is Mýrdalsjökull that is covering the volcano Katla, and then coming down this valley here. And you can see previous extent of the glacier in the glacier foreland. You can see indication of how big it was at the earlier time. So at the end of the little ice age in Iceland, end of 19th century, the extent of the glacier was out here, and then it has been retreating during the whole of 20th century with some advances, and I'll show that on a figure later on. But just keep in mind here how this glacier was filling all this valley here, and I'll show a few other figures of this glacier showing how much it has been retreating. So this is from 1985, and here is another figure showing how big it was in 2015, and already in 15 or actually earlier, a proglacial lake was forming. And this is what we see in many locations of the glaciers that come quite low, and they have been digging trenches in as they are advancing. The snouts are now being located into a proglacial lake that is forming, and that introduces a new danger or hazard in those places where the glaciers are retreating. And just to show, I want to just go one back here to show how the glacier looked previously. It was like filling here quite all the way to the brim of the valley here, and you can see the previous extent. And then here, this is how it looks in 2015. And then Oddur has put also together a series taken from a view spot kind of around this area here. So a series of photographs showing how the glacier has been retreating. This was in 1997, 2000, 2003, 2005, 6, and by 2010, the glacier had kind of went around the bend and is not visible anymore. So I just roll this back again and show the glacier retreating quite rapidly. And we have been observing the length changes of the glaciers since 1930. It started as a project of the Icelandic Glaciological Society already in the 30s. And this is when also a period many glaciers were retreating. So that caught the attention of many people in Iceland. And a group of volunteers have been working on locating the terminus position of quite a few glaciers. And now Hrafnhildur knows much better about the numbers and the number of people volunteering. But it's kind of like a participant science project that started in the 1930s that sometimes even farmers and their families, and now third generation of people going to the same glacier, are observing and making those length change measurements on many locations in Iceland and by the Icelandic glaciers. And this website here, sporðarkust.urfi.is, collects all this data. You can see each of the points is location of those measurements, and in some locations there are several measurements. And as an example of this type of measurements that you can find on this website, I show here Hofsjökull, where we were looking at before. It was retreating quite rapidly, and this is when the observation started in the 30s and all the way to around 1960. 60 to 95, it advanced quite a bit. And then at 1995, and since 1995, it's been retreating quite rapidly, retreated all the way back to where it had advanced in 1960. And then a few, like 500-600 meters in addition to that. So this is what we see as in most of the places in the world that we have glaciers, that the glacier, they are retreating quite fast. Just give you some images of the fieldwork. This is these are pictures from a student trip on Hofsjökull. Here you can see the lake in front of the glacier. And what I forgot to mention actually was the ash layer that is quite visible. So I'll just roll back a little bit because I think it's quite interesting that in the glacier we see the ash that was deposited on top of Mýrdalsjökull in the Katla eruption 1918, and now that is coming out and is actually quite a prominent feature in the glacier, and quite a lot of sediment, like ash layer, that is being melted out here at the front of the glacier currently. So now you see all the figures here again, and the students going up, and they help us carrying this, what we call a steam drill, and drill a wire into the glacier so that we can make ablation measurements. And this is a kind of measurements that we do in many locations on Icelandic glaciers. So I'm going to go through a few studies that have been conducted in Iceland in the past few years, and I start with Hrafnhildur study. So this is a part of her PhD project. She was gathering quite a lot of data, went into all kind of old archives, looked at old maps and historical and geomorphological data, maps from 1904 when the first maps were made in Iceland, 45 and 89. And then after that, there were some aerial images and also LiDAR surveys that helped her gather all this information for the southern part of Vatnajökull. So this is now the location square here, the red box. And this is where the highest mountain in Iceland is, Jökull and Hvannadalshnúkur. And you see here with the color coding how the glaciers have been retreating. The years are visible here. 1819, it kind of is the timing of the maximum extent, kind of what we can see most places, and the date 1819 has been put on the maximum extent, and then the retreat is being quite rapid. And because the subglacial topography has been measured, volume changes, which volume change estimates from those topographic changes have been evaluated, and this is what Hrafnhildur did for all those glaciers, and they're shown on next figure in a row. So from the west to east, so all those named glaciers here, along as well as those glaciers here on the eastern side, are shown on this figure here. So there are two figures. One shows the net loss to the left, and we see with orange letters and orange columns the volume loss in cubic kilometers, and the area decrease in the blue colors, and the numbers here on the right hand side. So the blue columns are referring to the numbers on the right hand side. And same data shown here as a relative loss. So here are now the numbers, the orange numbers are percentages, and the area decrease as percentage. And what we see also here is that the glaciers that are losing relatively little, as you would estimate from the figure here to the left, are losing almost 50, or this one has lost 50% of its volume and about 30% of its area. So the smaller losses are also like quite considerable part or portion of the total changes of those glaciers, outlet glaciers of Vatnajökull. So this image shows that about 20% area loss and up to 50% volume loss has happened since that maximum extent in 1819. And we carry on for Hofsjökull. The glaciologists at the Met Office, they have been observing, doing mass balance measurement, and Þorsteinn Thorsteinsson has collected the aerial change and the retreat history of Hofsjökull. And this, you can see here the area history, or the numbers for the area extend throughout the 20th century, and the estimated area loss for Hofsjökull is about 20% in the period 1890 to 2014. Then we also have geodetic measurements, and Eyjólfur and Håkín, they have done quite a lot of work gathering and putting together methods to create those geodetic measurements and estimating the volume changes for many of the glaciers in Iceland. And here is an example from Drangajökull. Eyjólfur published these results in 2016. Quite interesting maps, and Drangajökull is here located on the northern side of Westfjordur Peninsula. And what I quite like here is the figure showing here the surge on the northwestern side. So you can see both lowering here in in the central part, and then highering or the elevation rise at the edge of the glacier, indicating a surge. And in the following periods, we see that the terminus area has lost elevation, and then the accumulation area is increasing, has blue colors again. So quite a nice example of a surge here from Drangajökull. And then we see here two figures: the volume of the total ice cap and the mass balance showing similar to what we saw from the other glaciers, that there was a negative, or the retreat of Sólheimajökull showed that there was negative mass change up until 1960. It was close to balance from 1960 to 95, and then reduced back to or became negative mass loss after 1995. And several glaciers, 14 glaciers, were estimated by Hofsjökull, and this data is shown here in two ways. All the dots indicated on the map here, and each map is showing different periods, is shown with a line on this graph here. So each of those lines during this period is a dot on this map. And then the following period, all those dots are indicated with the lines here. So the similar history shows here as well up to 1960. There was overall negative, all the dots are red during this period. Then they are close to zero, close to mass balance, or close to balance. Some of the glaciers were positive, some were negative, and until 1990, I think here was 94, the change that the glacier mass loss was quite negative. And just to show that it's not, no, I just hit the page down towards the end, so I'll just have to go back. Sorry about this. Here. So what I wanted to show here, three different ice caps, one on the west, one in the central part, and one in the east. They're not quite in tandem, but generally the picture is the same, that it's close to balance and then became negative mass balance after 1995. And we also have direct mass balance measurements. So here's Finnur weighing a snow core. They go and measure about 60 locations on Vatnajökull and 20 to 30 on Hofsjökull and Drangajökull. Estimate the density of the snow layer, thickness and the density of the snow layer. And then we can create time series like this. Vatnajökull here, the biggest ice cap. You can see that it's a magnitude bigger than Hofsjökull and Drangajökull. And the time series in Drangajökull and Hofsjökull started in 1988, 97, and Vatnajökull in 1992. The blue columns indicate the winter balance, and the red, the summer balance, and the green line is the net balance. And the emerging picture is now becoming quite clear that after 1995, we had negative mass balance. What is standing out here is the very negative mass balance in 2010, when we had the eruption in Eyjafjallajökull, spreading a lot of ashes over the surfaces and enhancing the mass, or enhancing the melting at the surface. And we have here a very high negative or highly negative mass balance during the summer. And after 2010, the mass loss rate has reduced, and we even had some periods or some time or a year with a positive mass balance, and a few years that were very close to balance. And I would say like more variability during the time after 2010. And if you look closer into this figure here, we show that 2014-15 positive year for all the glacier was resulting both from more incoming, more winter balance, and quite a poor summer. So the summer 2015 was relatively bad. There was a lot of clouds and very cool summer, so the melting wasn't very, or it was less than average during that summertime. I just want to show that the last column here is not quite confirmed, but Thorsteinn and Finnur gave me those data for Finnur to make this figure, and we just put them a little bit in grayish color because they have to be confirmed, the latest numbers. But what we see here is that there are now years again that have quite a negative mass balance, again after the period where the mass balance was close to zero. And Finnur has made or put this data into cumulative mass balance. And then we can clearly see that the smaller glacier, Hofsjökull and Drangajökull, they're losing mass at a faster rate than the bigger Vatnajökull. So Vatnajökull is losing about 0.5 meter a year, and Hofsjökull and Drangajökull about 1 meter a year. So the mass loss is faster for those smaller glaciers. They're both lying lower in the landscape and are smaller as well. So that's interesting to observe that not all the glaciers are losing mass at the same rate. And further figures from Finnur, he's been working with the data for decades, and he's plotting a very interesting figures. And here, those are showing the winter balance for the period, or for the winter 2019 to 20. And what I like to show or point out here is that at the lowest level, where the glaciers are very close to sea level, the mass balance is very close to zero and even negative in some locations. So not positive mass balance during the winter time at the lowest elevation. But we have negative mass balance almost all the way to the highest peaks of Vatnajökull, and the balance you see here, the difference between the incoming and the outgoing mass balance, and the equilibrium line is indicated with a green line here. And the plot shown, or the two plots here on the right-hand side, show the net balance for the different outlet glaciers as a function of the accumulation area ratio and the equilibrium line altitude. And it's quite interesting to look into this data and show that the glaciers have very similar slopes, but each of the glaciers have distinct line on those plots. And looking at each of the outlet glaciers of Vatnajökull, and some of you may already know the names of the glaciers and where they are located, but just looking at those figures together, I find this quite interesting that we see the Drangajökull and Brúarjökull, and also the Jökull, those three glaciers that are shown here are the three glaciers that are the most kind of inland glaciers. So they are further away from the coast, and they experience more continental climate than the glaciers that are closer to the coast and have more maritime climate. So you can see that the cumulative mass balance for the more inland glacier is a lot less than the maritime glacier. So we observe this, that the maritime glaciers have a much more mass throughput, and they are responding to the increased warming faster than the more inland glaciers. And yet another figure from Finnur's plots. And I find this is actually quite interesting plot to look at the winter balance here on the left figure and the summer balance on the right-hand figure, plotted against the net balance. And drawing a line through the data set, we actually get quite, not coincidentally, but we get nicely the same value for the crossing point with the zero net balance, that in order to maintain mass balance for Vatnajökull, we would need 1.74 meter water equivalent mass balance, and the same goes, or the similar or same number for the summer balance, that we would lose that in order to keep the glacier in balance. But the average over the period of measurements is about 93% of this, the amount that is needed to maintain the glacier. So nearly, but almost incoming mass would maintain the glacier, but there is a lot more, almost 20% more mass loss than would be maintaining the glacier. So the mass loss is, of course, mostly because of the melting of the glacier, but also because there is a little bit too little incoming mass to maintain the glacier. And then gathering all the data, this is what we have done in a recent study. We got all the data that we have been gathering together in Iceland. So Hrafnhildur at the Met Office, he has gathered all the area changes of all the glaciers in Iceland, published in a very recent Jökull paper, showing the outlines and the areal changes of all the glaciers in Iceland. So that's a quite interesting paper I want to highlight here. And the data from this paper and all the volume changes that we have were used to figure out the total volume of the biggest ice cap at the time when they had the largest extent. So this figure shows, and you can see that there are actually three figures here. So the one is the big one here, with the data for Hofsjökull and Drangajökull in the blue and green dots here, and the line that goes through the points for volume and area for Vatnajökull are here on the outermost end of the graph. And there's a zoom up for Vatnajökull data here and for Hofsjökull and Drangajökull data. And all the points that are shown here, those are data where we have both the area and the volume of the glacier, because we have a very good bedrock data, so we can estimate the volume of the glacier or the ice caps. And then we are using the area volume scaling to estimate what the volume was at the maximum extent at 1890, both for Hofsjökull and Drangajökull, and then for Vatnajökull here. So we have Eyjólfur and Finnur, they were kind of doing estimate, because the area of Vatnajökull is also including area changes because of searches. So there had to be some kind of error or assumption of how big that change would be. So that's the range that we have here for the area volume curve here. So the volume would be one of those, or in between those three dots here, given the uncertainty that the searches put on the area for Vatnajökull. And all this data was then used to estimate the total mass balance history of all the glaciers in Iceland for the whole of 20th century. So here we put the data from the geodetic measurements. So these are the data from Hokkin. The mass balance measurements you can see here as blue columns. And then the estimate based on the volume area scaling go back all the way to 1819. And we see also for Drangajökull, Finnur had collected some photographs and aerial photographs and maps for Drangajökull, indicating that there was actually also for Drangajökull quite a negative mass balance period in the 30s for Drangajökull. And that is reflected, or these mass history of the glaciers in Iceland reflect actually the temperature history. These are air temperature history from Stykkishólmur, summer temperature, showing that it was warmer in the 30s and up to 40s and 60s. Then it got a little bit cooler, and then after 1995, the temperature went up, and that caused all the glaciers to respond and get smaller. And these are then the back calculated volume changes for all the glaciers based on all the data that is presented on the left-hand side. And that's, we also have to take into account, and this is what Thomas has been working on, is that the non-surface mass balance is not negligible. So we have to take into account that melting due to combination of geothermal activity and volcanic eruption actually are quite a considerable part of the mass loss for Icelandic glaciers. And Thomas also estimated the energy dissipation in the flow of water and ice for all the glaciers, and also the calving fluxes, and that's mostly Breiðamerkurjökull in the study that he presented there. And the total runoff due to the non-surface mass balance is about 2 cubic kilometers per year. So that is quite considerable, and if we compare to the total numbers in the next figure, we'll see that it's actually non-negligible part of the mass balance. But it's very variable, and you can see that it's only 5-6 centimeters for Drangajökull and Hofsjökull. It's actually quite a high number for Mýrdalsjökull that is overlying the active volcano Katla, and there are quite many cauldrons where there is active geothermal melting at the base of Mýrdalsjökull. And the same for Vatnajökull. The northern and western side of Vatnajökull has a lot less non-surface mass balance than the southern part of Vatnajökull. And this we combined with the data that I showed you before to produce this combined record of all the glaciers in Iceland. And we, of course, don't have that high time resolution for the first part of the century, but the total mass change rate based on the volume area scaling is about 16% of the 1819 volume, which is about 1.5 millimeters of sea level rise equivalent. And half of that mass change happened in the period after 1995. So that's kind of the global history, or the total history of the mass change for all the glaciers in Iceland. And we can compare that, and this is the last figure in the new publications that we had out recently, with other estimates, with records based on the surface mass balance. That's Michael Semp's estimate from 2019 and 20. Those are shown here with green and kind of mossy color, because those were 2 extra points that he provided in a separate publication. And also from Wouter's data that is based on grace, that the variability is quite similar in all these records, but the interpolation or the extrapolated surface mass balance measurement are generally smaller negative than our estimate. And that we understand because that doesn't include that non-surface mass balance, among other things. And the grace data, that is sometimes over and sometimes underestimating or larger or smaller than the estimate that we have. And this can also be understood that the grace footprint is actually quite large. And there is, because of the isostatic rebound, other mass transport into the area, because the crust is being lifted up as the glaciers are getting smaller. So the grace cannot really distinguish between the mass changes because the mass of the glacier is changing, or because of the crust or the mantle mass movement underneath it. And we have also in 2014 an eruption in Bárðarbunga that was transporting mass from underneath the glacier outside the glacier. But I think the footprint of the grace data would actually be with or like outside that range. So we know of an example that there was actually quite a big mass transportation that grace probably would not be able to see, but we don't actually, or actually I don't know, but I don't know if other people have been able to interpret what is caused by mass changes of the glacier and what caused by the tectonic activity. And one of the last, or these are now coming towards my end, towards the most exciting part of the talk, and I see that time is flying actually quite fast. But I want to point out also work from Andri Gunnarsson. He's been looking at the albedo of the Icelandic glaciers. He's collected all the MODIS data, very high spatial and temporal variability of the albedo. And this is a very important input when we want to model the mass balance of the glacier. And I just want to highlight this paper. There's a lot of interesting things to see here, but I carry on because the albedo is then used to estimate the mass balance. And here are the results from Louise's. He used a regional climate model, the Harmony, at a 2.5 kilometer resolution. And this plot shows her results with a dotted line and the mass balance observations that I showed you in the previous slide with the solid lines. And what we observe here is that the model is simulating the variability actually quite well. And we can then extend the time series back in time to the beginning of the era interim data that is used to force the regional climate model. And then we are using the model, or Louise used this model to make a projections for the future of Vatnajökull. And here are the results from Vatnajökull. There are 2 scenarios, the one to the left and the other one to the right, RCP 4.5, that has about 2 degrees warming until 2100, and the RCP 8.5 that has about 4 degrees warming until 2100. And Louise had simulations from the Cortex experiment that run until 2100. So you see here 2100 is located here on the graph, and then she repeated the last 20 years of this century for about 200 years more, because we saw that at year 2100, Vatnajökull had not reached kind of like the turning point that it was starting to reduce the mass loss yet. So she decided to continue the last 20 years of this simulation. And then what we see from those simulations is that actually for Vatnajökull, that has a very long response time, it will take a long time to kind of for Vatnajökull to adjust to several decades, actually, maybe more like 1 or 2 centuries, for it to adjust to a new climate. And the take-home message from these simulations is that it really makes a big difference for Vatnajökull that we keep the Paris Agreement. So if we manage to limit the warming at below 2 degrees and preferably 1.5 degrees, then 30 to 60% of Vatnajökull's current volume may actually survive. And that's indicated here with the yellow area here on the lower figure. But if we don't reduce our emissions and we get about 4 degrees warming at the end of this century, then it's likely that most of Vatnajökull, maybe 20–30% of Vatnajökull, will survive. And that's again ice will be left in those areas that are indicated with yellow here. And just to show those 2 scenarios here, the top figures are showing the bedrock and the surface topography, and then the RCP 4.5 scenario here to the left, and then the RCP 8.5 scenario here to the right. So the message from these simulations is that it really makes a difference what the emission scenario, what the future of Vatnajökull ice cap will be. So just to summarize the presentations that I had prepared for today, until we go very briefly into current excitements, I've already said all this, that the glaciers are rapidly responding to changes in climate. We had this slow retreat onto 20s. We had high mass loss rate in the 30s to 50s, period where it was close to equilibrium or slightly positive mass balance for some glaciers. And then after 1995, all of the glaciers experienced mass loss with a large variability, but reduced mass loss rate after 2010, but also with high variability. And there are several reasons for the increased mass loss after 95. Warmer and sunnier summers, so we have a longer ablation season. We have warmer winters, so more of the precipitation falls as rain. So that means that there is less snow low on the glaciers and dirty ice appears earlier from beneath the snow in spring. But a big correlation is the ocean temperature around Iceland. So the glaciers are really feeling the ocean temperature and responding to changes in the ocean temperature quite a lot. And then the last point is really what I was showing in the last slides, that it really makes a difference for Vatnajökull's future, what the emission scenario will be. So I think that's a strong message to give, that we should really try to follow that Paris Agreement. So I want to spend a few minutes and I thank Eyjólfur and Krista for making it possible to show those figures. And I was looking for an overview figure to show you the kind of setting of Vatnajökull and how the location is. And I found, and now I don't want to, I was thinking that it could be misunderstood, but I want to show here an old photograph from 1996 when there was an eruption. There is no eruption yet in Vatnajökull, but this is in 1996. And I just had this old aerial photograph showing the Grímsvötn caldera here, kind of hiding behind the steam from the volcanic eruption here. But this is really where the subglacial lake Grímsvötn is located, and it collects meltwater, and the meltwater is being collected or gathered in the subglacial lake. And this is what we are then observing, that the lake level and the ice shelf on top of it is rising until very recently it started going down again, indicating that the water was going out of the lakes. So here's another picture. This is the caldera brim, and the subglacial lake is underneath this ice shelf here. And this is around this location is where the GPS antenna is that we are observing. So just an overview picture here. This is the caldera brim here shown with a dark color. The water is leaving the lakes here on the eastern side of the caldera brim, and then somehow going underneath the Skeiðarárjökull. And I know Gwen Flowers is probably interested in knowing how the water is going underneath. Many people would be very eager to start thinking about how the water is then going in either channels or in water sheets underneath Skeiðarárjökull, and then appearing here at the edge of Skeiðarárjökull, going into a river called Gígja. And the new data here, this is the data from the antenna sitting on the ice shelf being raised because there is more meltwater going up in the summertime. So the figures for the plot starts here in July, August, and September, and the rise was starting to slow down, as we could see here. And at the date of Eyjólfur's presentation here on the 12th of November, he was very right in saying that it was imminent that the Jökulhlaup would start. And I think we could say that during the time when he said that, that's when it started to lower again. So the water was starting to trickle. And then a few days later, it started going very rapidly out of the lake. And now already the lake level has lowered by several meters. And because Eyjólfur has such good data of the area of the lakes, they have now computed the discharge, the amount of water leaving the lakes. So this is now a figure I got from the net today. And you can see how rapidly the discharge is rising now up to about 800 cubic meters per second. And I was listening to Eyjólfur today predicting that the discharge rate might actually increase to about 3,000. And I think the discharge rates in the Jökulhlaup in '96 was much more than that. Maybe Eyjólfur can help me. I forgot the number. It's probably a magnitude larger or for the discharge rate after the 1996 eruption that had a lot more water than gathered in the lakes. And I got this figure also from Eyjólfur. This is a projection of the rise in the water discharge. So the water is leaving the lakes, and these are the data here plotted. And then the exponential function that is being fitted, showing that the discharge rates might actually rise up to about 3,000 cubic meters per second to reach its maximum. And I think the projection for the maximum discharge rates is for Sunday, I think, and please correct me if I'm wrong. And I just want to put here the references that I've been using, and those are all very recent papers that have come out in the past couple of years that we are very proud of, that so much has been published. But the final thing I wanted to show you is the water coming to the rivers. And now I want to stop sharing, and I want to share not this one, I want this one here to show you. This is a webcam from the river in the last few days, so you can see that the water level is rising quite rapidly now. So the water is now entering the river, coming from the subglacial lake in Grímsvötn. I'll just show you this again, because now you see how the water was before the Jökulhlaup started, and now quite a lot of water has come into the river. And in the news this evening, they said that the river level had risen about a meter. I'll show it once more. It's a quite impressive amount of water coming out now. So I thank you very much for your attention, and thank you for coming and listening to the talk. And I'm happy to take any questions you may have.
Fantastic. So thank you very much indeed. And thank you so much for showing us the very, very, very latest results. It's really exciting. So what we usually do is we ask people to indicate in the chat if they have any questions. Olga, I think you got there first. Do you want to unmute yourself?
I'll try to. My connection is great, so if I'm breaking, David, could you please just read the question? If I'm all right, then yeah, the question is about the slide, the second before the last one, about the discharge, the rate of the discharge. So it appears that you have daily cycle, like the red dots go up and down. Any thoughts on that?
Yes.
And by the way, fantastic talk. Thank you.
Yes, well, the daily cycle is probably just a noise in the GPS data. So this is really the antenna sitting on the surface of the lake. And we've been discussing this, that it could be interesting to know if there was some diurnal cycle in the lake level, but it's so small compared to what now the lake level is getting lower. And Eyjólfur convinced me that this is just noise from the GPS, and it could be ionospheric disturbance that would have daily cycle as well. So I think we should not concentrate on this diurnal cycle at all, but it would be interesting if there was a daily cycle in that signal, but I think we would have to be really careful to interpret that from the GPS data that would possibly have some ionospheric disturbances at the same frequency.
Thank you. That's great. Thanks.
So are there any more questions? I was wondering whether we're going to see any destruction of infrastructure, Tolly, in the way that, was it 1996? It seems so long ago. Or is this just a much smaller event and we shouldn't?
This is a much smaller event, and it also is flowing in a different river system because the glacier has retreated so much that it's not going into the same river anymore. And well, first of all, the amount of water is much less in the 1996. That was after eruption, that there was a lot of melt because of the eruption, and a lot of water had collected in the lakes. And this is I would say, I mean, this is not following an eruption, and it's sort of like I would say kind of a normal, I'm hesitating to use the word normal, but it's kind of like a Jökulhlaup that comes because of the melt water that is collected in the subglacial lake. So nothing particular as if there was an eruption.
Thank you. So are there any questions from anyone in the audience? I don't see any on Hester, go ahead.
Hi, Tolly, fantastic talk. I actually don't have a question about the science, but about the scientists. So all the work, I think it's really fantastic, like all the different aspects that come out of Iceland, and various people have worked for a very long time and a lot of different things. So I just kind of wonder what is kind of the secret of like people having worked there for a really long time, sometimes shifting the focus a little bit. Do you have kind of a central, like every 5 years you have a really big group meeting to think about what's happening in the future as the whole community of Icelandic scientists, or is it just going kind of naturally in the right direction?
Well, that's a very good question. I think, you know, as just looking back, and now I start to feel I'm a little bit middle-aged, but I've been, you know, part of the group since I was an undergraduate student. So I've been watching this, and I think one of the secret is that there are so many projects and there's so much going on that there is a lot of projects for everybody, and endless really. And you know, we have searches, and we have Jökulhlaups, and we have now the response to climate change, and we've been, and Helgi and Finnur already started decades ago measuring with radio echo sounding, developing the method of measuring temperate glaciers with radio echo sounding methods, and that gives us brilliant data to work with when we want to model. And subglacial water and water discharge, like Gwen was working on when in her postdoc project in now some decades ago, but I think it's still quite actual now that we are watching like water traveling under the glacier, and in those Jökulhlaups we are actually collecting fantastic data, and there's a lot of data that we have to work on. And I think maybe the secret is that there are so many projects going on, but I think there are also very brilliant people working here, and the atmosphere is quite nice, and we have glaciologists both at the university and the Met Office, and we work quite nicely together and are combining the efforts. So I think that's really a nice and very good position to be in, that many people, many projects, and we are working well together. So that's actually quite nice.
Yeah, thank you. And you're also not protectionist. So there's also a lot of foreign people that come to Iceland and work at the same time. So thanks.
Ian.
Oh, yes, thank you very much. That's a great talk, lots of useful information. I wonder if you can summarize the change in ELA for the whole of Iceland as an average, say since 1980 and since 1890?
I think that it's actually quite variable, like depending on if you're on a glacier very close to the ocean or inland. They are like I was showing with a different cumulative. So I don't think there is like a common record, but I guess if your question is if you want to get from the different outlet glaciers or like a one history. So I think if there was from different outlet glaciers, they were a little bit variable, and I was trying to show that with the data from Hofsjökull, from the different smaller glaciers, that they're not all responding in tandem. So some are sometimes losing more mass, and they are not always like responding to the same or responding similarly. So I think here the distance to the ocean is really a key. So that may actually influence that the ELA history. But I haven't looked at it myself, so I'm kind of hesitating. I'm maybe like a politician, not answering the question. but I think that would be actually something that would be interesting to look at. But my suspicion is that it would be quite different from the different glaciers.
Right, thank you very much. Clearly you showed that the recession has been throughout all of these glaciers over the century or so. But I take it that the main contrast you're talking about is between the coastal facing glaciers and the more inland outlet glaciers.
Yes, so maybe I should say that the history is that the ELA has been rising as the temperature is increasing, but the rising rate is probably different. So this is what I started to thinking that, you know, clearly as the glaciers are retreating, the ELA is getting higher. So that probably is like the general history. But during the period 1960 to 95, the ELA must have been lowering because the glaciers were advancing during that period. Some of them were close to balance. So then at least the rising rate would have stopped during that period. So I think that would be then the temporal time when the equilibrium line would stay at the same level. But after 1995, it started rising again. So I think that would kind of be the general history.
That's great. Thank you very much.
Thanks, Tolly. We have a question from Roland on the chat. Do you want to unmute yourself, Roland?
Hi, Tari. So now I have to actually try and pronounce that. Great book, Tolly. Particularly fascinated by your postscript, because since I've been following the Gjálp, I'm not going to say it properly, a volcano with enthusiasm, I noticed that the online commentators, having lost their volcano to get excited about, have started focusing on this Grímsvötn drainage, and they seem to be hoping that this means there'll be an eruption there. Is this just idle speculation?
It is speculations, but there are history of both eruption coming in the wake of a Jökulhlaup and no eruption coming in the wake of a Jökulhlaup. So we don't really know what's going to happen. And Páll Einarsson, a seismologist here, he's been looking at the seismic tremor, and currently we only see like the tremor that he associates with water leaving the lakes. And as soon as he sees tremors that could be indicating eruption, he will let us know. But it really is impossible to tell what's going to happen in the coming days. But there is an example of when the lake level has lowered, I think, halfway down, and I think that's a few tenths of meters. I'm really bad with numbers. Maybe if Eilur is still there, maybe he could help me out. But there has happened that as the lake was half emptied, an eruption was initiated. But we don't really know if that's going to happen this time. It is possible, but so it's something that we are watching very, very closely.
Okay, could I just follow up? Does that mean the general feeling is that it's not volcanism leads to Jökulhlaups? It's more the other way around, that the sudden loss of the load there triggers the volcanic activity.
It has happened, but it not necessarily follows, eruption doesn't always follow Jökulhlaup, yes.
Okay, thank you very much.
Fantastic. So are there any last questions for Tolly? I think we're out of questions there, so I'm just going to hopefully share the slide advertising next week's seminar. So next week we have a group of undergraduates from the Juneau Icefield Research Programme coming to the seminar to talk. So please come along and support the earliest career researchers we have, the undergrad researchers. So that will be the last seminar before Christmas as well, and before AGU. So thank you very, very much indeed, Tolly. That was fantastic, really exciting talk for us all. And thanks to everyone for coming, and hope to see everyone next week. So thanks very much.
Thank you.
Really enjoyed that. So thank you very much indeed.